Moving on, allow me to tie the previous sections into a discussion about scientific calculators. Long story short, your calculator can do all this calculation for you, but you've got to set it up properly and know how to use it. This section operates under the presumption the viewer is familiar with a Texas Instruments TI-89 Titanium Edition scientific graphing calculator. If you lack familiarity with this calculator, I recommend hitting up the tail end of the DC Math lecture, available at the Big Bad Tech channel. If you've got an alternative equivalent scientific calculator that can perform the same functions, that's great, but you are on your own. If you don't know how to set up your equivalent calculator and perform the exact same functions I'm doing with a TI-89, by all means, get yourself a TI-89 or bust out your user's manual for your particular calculator and figure it out yourself. First, your calculator needs to be in the proper mode. As detailed in the aforementioned lecture, recall I emphatically recommended the calculator be placed in specific operational modes. If you've done so already, you're in the clear, but if you're not, here's a procedure to do so. The single most important key on the TI-89 is the mode key. This accesses three basic setup screens accessible via the F1, F2, and F3 keys below the main screen. If someone tosses you a TI-89 brand new out of the box, you should be able to set it up in less than 10 seconds and be ready to rock and roll. This is equivalent of being able to field strip, repair, and reassemble a firearm in a combat situation. The TI-89 won't work well if it's in the wrong mode, and you need to be able to get it into the right mode as quick as possible. The first F1 screen has four options that need to be set up properly: display digits, angle, exponential format, and complex format. Walk down to the display digits using the down arrow key and then press the right arrow key to access the menu. There should be a list going from 1 to Q. Walk down the list using the down arrow key. The option I'll choose is E, float. Not float 1 or float 12, straight up float. Option E, between D fix 12 and F float 1. Press enter to save this option. Using the float setting, the calculator spits out answers using as many decimal places as it can, and you're free to round it to the degree of precision required. Most of the time, I tell my students to use the most appropriate engineering prefix and just round it to the tenths place. Don't make a big deal out of this. Use the most appropriate engineering prefix and just round it to the tenths place. I know if you're right or wrong. Walk down to angle using the down arrow key and then press right arrow to access the menu. Walk down the list with a down arrow key. The option I'll choose is 2, degree. Press enter to save this option. This entry is essential for this topic. Walk down to exponential format using the down arrow key and then press the right arrow key to access this menu. Walk down the list with a down arrow key. The option I'll choose is 3, engineering. Press enter to save this option. Walk down to complex format using the down arrow key and then press the right arrow key to access the menu. Walk down the list with a down arrow key. The option I'll choose is 3, polar. Press enter to save this option. Some of these entries in the first page should be familiar to you given our previous discussion, and we'll examine complex format in later lectures. However, directly related to today's lecture, the angle setting establishes degrees as our unit of choice, not radians. Your math teacher may prefer radians, but they're wrong. Angle format must be in degrees for this course. I'll show you how the calculator does conversions between radians and degrees in a moment. Moving on to the second F2 page of the mode function, one can pretty much ignore everything with the exception of the last option, exact versus approximate. Walk down to exact versus approximate using the down arrow key. Press the right arrow to open up the menu options. Use the down arrow key to walk to option 3, approximate. Press enter to select this mode. Most of the entries on the third F3 screen of the mode function aren't super important. In summary, first page accessible using the F1 key, display digits, E, float, angle, 2, degree, exponential format, 3, engineering, complex format, 3, polar. Second page accessible using the F2 page, exact versus approximate, 3, approximate. Assuming your calculator has these settings, navigate to the home screen and feel free to follow along. Let's examine unit conversion between radians and degrees using the scientific calculator. First, to convert between radians and degrees and vice versa, one could always perform the unit conversion using the manual procedures mentioned previously. The calculator, however, can do this for you with a minimum of keystrokes. Given your calculator is in degree mode, it assumes every numerical entry is in degrees and not radians unless explicitly stated otherwise. Let's deal with the conversion from degrees to radians first. Let's say we want to convert 30 degrees to radians. Enter 30. The calculator knows you mean 30 degrees, not 30 radians. Then press Catalog. Walk down the catalog entry until you find an arrow key pointing left to right that says Rad. Then press Enter to select it, and press Enter again to perform the conversion operation. The calculator returns that 30 degrees is roughly equivalent to 0.5236 radians and signifies it's currently violating the previously agreed upon degree standard by enclosing the value in parentheses and putting the superscript R next to it, meaning radians. The conversion from radians to degrees is essentially the opposite. Given your calculator is in degree mode, it'll forcibly reformat everything you feed it into degrees, providing you tell it that what you're feeding it is in units of radians. To tell the calculator you're entering in radians, enclose the value in parentheses and put the superscript R after it, meaning radians. When you press Enter, the calculator reformats the entry into degrees. Let's say we want to convert pi over 2 radians to degrees. Enclose pi over 2 in parentheses and then press Catalog. Walk up or down the catalog entry until you find the little superscript R. Press Enter to select it, and press Enter again to perform the conversion operation. The calculator returns that pi over 2 in radians is 90 degrees, as we'd expect. Note 90 degrees doesn't necessitate units for clarification because we've established degrees as the unit of choice. Really, the only way to get this process wrong is to mistakenly enter radians without telling the calculator you're using radians. Unless explicitly specified using parentheses and the superscript R modifier, the calculator assumes everything you throw at it is in units of degrees. Put your understanding of unit conversion using the scientific calculator to the test by converting between the following measurements. If you're given an entry in degrees, find it in units of radians. If you're given radians, find it in units of degrees. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. 3 radians is roughly equivalent to 171.9 degrees. Given 3.14 radians is halfway around at 180 degrees, 171.9 degrees would be just a little shy of 180 degrees. 80 degrees would be roughly equivalent to 1.4 radians. 17 pi over 12 radians would be equal to 255 degrees. And finally, 20 degrees is roughly equivalent to 0.35 radians. Moving on, let's now discuss how to perform the sine and inverse sine function using the scientific calculator. Again, given your calculator is in degree mode, it assumes every numerical entry is in degrees and not radians unless explicitly stated otherwise. To determine the value of the sine function at specific angles, press second sine, the light blue alternate entry above the Y key. Enter the angle of interest, close the parentheses, and press Enter. The calculator will return the value of the sine function at that angle. For example, let's use the calculator to determine the value of the sine function at 30 degrees. Press second sine, enter 30, close the parentheses, and press Enter. The calculator returns 0.5. Too easy. Put your understanding of the sine function using the scientific calculator to the test by determining the following values to 4 decimal places. It may help to locate these positions on a unit circle and determine how the sine function, the height above or below the horizontal x-axis, relates to this position to check your work. By all means, pause the lecture and try this on your own. Pay attention to example problem 3. Don't walk into this easy trap. If you're tracking, you should have obtained the following values. The sine of 34 degrees is approximately 0.5592. 34 degrees on the circle and the sine function would be right about here. The sine of 247 degrees would be approximately equal to negative 0.9205. This position on the circle and sine function would be right about here. Note our value is negative because we're below the x-axis. The sine of 13 pi over 12 in units of radians would be equivalent to the sine of 195 in units of degrees. This value is negative 0.2588. This position on the circle and sine function would be right about here. Again, note our value is negative because we're below the x-axis. Additionally, note we first needed to convert from radians to degrees because our calculator assumes every number we enter is degrees. Finally, the sine of 900 degrees equals 0. At first you might be surprised by this, but think about it. One full revolution is 360 degrees. Two full revolutions is 360 plus 360, or 720 degrees. Go one more half revolution, or an additional 180 degrees, you've got 2.5 revolutions, or 900 degrees, and you're back on the x-axis on the far left side of the circle. It makes sense. Sine of 900 degrees equals sine 180 degrees, which equals 0. Is there a trigonometric identity you can memorize? Yes, there is. But why would you do so? Look at it. Circles and sine waves have inherent symmetric and repetitive properties that you can't not see if you're paying attention. Using the sine function in the scientific calculator should be easy. Here's something that will challenge you. Most scientific calculators can also perform the inverse sine operation. The inverse sine, written sine to the -1, is essentially the sine function in reverse, meaning at what angle will have this sine value. To use the inverse sine function of the TI-89, press diamond inverse sine, the light green diamond entry above the Y key, enter the value of interest, close the parentheses, and press enter. The calculator will return the nearest angle at which the sine function achieves this value. Note, nearest angle doesn't necessarily mean first and only, as we'll learn in a moment. Additionally, note, since the sine wave peaks out at 1 unit, asking the inverse sine function at what angle the sine function achieves values greater than 1 or less than -1 is like asking your lazy lab partner to show up to class on time and well prepared, i.e., it's not going to happen. The inverse sine function is valid only between +1 and -1. To keep this easy, let's first perform the inverse sine for 0.5. We're essentially asking the calculator what angle has a sine value of 0.5. Press green diamond, inverse sine, enter 0.5, close the parentheses, and press enter. The calculator returns 30 degrees, as we'd expect, because yes, as we previously demonstrated, the sine of 30 degrees is 0.5. The problem is, this answer is wrong, and that it only gives us the nearest angle at which the sine function achieves this value. Recall that multiple planes of symmetry exist within the sine wave, and the sine function also achieves a value of 0.5 at 150 degrees. Is there a trigonometric identity you can use to remember this relationship? Yes, there is. But why would you waste time memorizing trigonometric identities when you can just look at a sine wave's first and second quarter and realize they're symmetric? The rising positive first quarter's 30 degrees is essentially equivalent to the falling positive second quarter's 150 degrees. Really, there's only 2 points on the whole sine wave where a single inverse sine value is correct. Notably, an inverse sine of 1 is achieved only at 90 degrees, and an inverse sine of -1 is achieved only at 270 degrees. All other values between 1 and -1, 0 included, should have 2 valid answers for inverse sine. Again, there's no shortage of trigonometric identities to memorize, but doing so is far less productive than simply looking at a sine wave and realizing the simple truth. Put your understanding of the inverse sine function using the scientific calculator to the test by determining the following inverse sine values. By all means, pause the lecture and try this on your own. Note, unless you're being asked to solve for the inverse sine of 1 or -1, the calculator is going to give you only one answer, and it's up for you to determine the other. Note the vertical planes of symmetry for the rising and falling portions of the waveform should allow you to find the second value. It may help to locate these positions on the sine function to check your work. Pay attention to example problem 2. You will encounter some weirdness, but you should be able to fight your way out of this paper bag if you've got a reasonable degree of mathematical competency. If you're tracking, you should have obtained the following values. The inverse sine of 0.8 yields 53.1 degrees. Given the vertical plane of symmetry about 90 degrees, one would also expect the sine function to achieve a value of 0.8, also at 126.1 degrees. Corresponding points in the unit circle support these answers. The inverse sine of -0.6 equals -36.9 degrees. What on earth does this mean? Given we've been defining positive angles as counterclockwise travel from our agreed upon point of origin, it it makes sense that negative angles are merely clockwise travel from our agreed upon point of origin. Negative 36.9 degrees would be equal to positive 323.1 degrees. Given a vertical plane of symmetry of about 270 degrees, one would also expect the sine function to achieve a value of negative 0.6, also at approximately 216.9 degrees. Corresponding points on the unit circle support these answers. Inverse sine of 0 yields 0 degrees as we'd expect. This is the zero crossing going positive point of the sine wave. The corresponding point is the zero crossing going negative at 180 degrees. Because I threw you a couple curveballs in that first batch of example problems, here's another set just to make sure you're on target. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. The inverse sine of 0.2 yields 11.5 degrees. Given the vertical plane of symmetry about 90 degrees, one would also expect the sine function to achieve 0.2, also at approximately 168.5 degrees. Corresponding points on the unit circle support these answers. The inverse sine of negative 0.4 equals negative 23.6 degrees, which corresponds to positive 336.4 degrees. This nearest angle would be right here on the rising side of the negative half. Given a vertical plane of symmetry around 270 degrees, one would also expect the sine function to achieve negative 0.4, also at approximately 203.6 degrees. Corresponding points on the unit circle support these answers. At this point in time, you may be rightly asking yourself, what the hell does all this sine wave math have to do with electricity? Let's take a moment to answer this very pertinent question. At a very fundamental level, circular rotation is the origin of both the sine wave and sinusoidal voltage. Consider a generator shaft driven by some outside physical force like expanding steam, moving water, or blowing wind. Attached to this shaft is a magnet with a north pole and a south pole. This rotating assembly, consisting of the shaft and magnet, is appropriately enough called the rotor. Outside the rotor is a stationary set of windings called appropriately enough the stator. Every time the rotating magnet passes by the stationary coil, a voltage is induced across the terminals of the coil, proportional to the rate of change of the magnetic field and the number of turns in the coil, according to Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction will be detailed in later lectures. However, for the purposes of this lecture, the generation process can be simplified as the following. When a north pole is close to the stator, let's assume it generates maximum positive voltage. And when a south pole is close to the stator winding, let's assume it generates maximum negative voltage. As the rotating magnetic poles approach or recede from the stator, the circular rotation and resultant induced voltage waveform can be modeled as a sine wave. Given the magnet starts operation at 0 degrees with both the north and south pole equidistant, no voltage is generated. However, as the rotor is driven counterclockwise, the north pole gets closer and closer to the stator, and induced voltage peaks out at 90 degrees. As the rotor continues to drive counterclockwise, the north pole gets further away. The induced voltage during this quarter is still positive, but decreasing. At 180 degrees, the north and south poles are again equidistant, and induced voltage is 0 volts. The other half is essentially a repeat of the first, only a negative voltage will be generated since the south pole is on the business end. As the rotor continues to drive counterclockwise, the south pole gets closer and closer to the stator, and induced voltage bottoms out at 270 degrees. As the rotor continues to drive counterclockwise, the south pole gets further away. The induced voltage during this quarter is still negative, but decreasing in magnitude. At 360 degrees, or 0 degrees, we've done a full circle, and the north and south poles are again equidistant, and the induced voltage is 0 volts. The process then repeats itself. By the way, I have taken great liberties in this simplification that I'll come back to correct in later lectures. For now, just put your hand on top of the internet and repeat after me. I, state your name, believe. The point being that the very act of generating voltage has its origins in circular motion, and no wonder the resultant voltage output is sinusoidal in nature. Additionally, we'll learn in later lectures that given sinusoidal voltage input, output current is also sinusoidal in nature for passive electronic components like resistors, inductors, and capacitors. In summary, everything is sine waves from this point on, and you've got to know how sine waves work if you wish to succeed in AC circuit analysis. This being said, if everything's a sine wave from this point on, we might be able to derive some usable shorthand that saves us time and effort. All this and more awaits. Until then, this concludes this introductory lecture on circles and sine waves. In conclusion, this lecture examined properties of both circles and sine waves. We learned the significance of radians and degrees and learned to convert between these two positional measurements. We examined circular origins in the sine wave and learned to calculate the sine function at different angles. Additionally, we learned how to perform both the sine and inverse sine function using a scientific calculator. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.